Hello and welcome to section 1.4. Today we're going to look at continuity and one-sided limits. This is going to be the first part of 1.4 and tomorrow we'll do the second part. So in section 1.4 we're going to look at continuity at a point on an open interval. We're going to determine one-sided limits and continuity on a closed interval. We'll look at the properties of continuity and then we're going to look at the intermediate value theorem. So, to get started, we're going to look at the continuity at a point on an open interval. And before we can do that, the thing with continuity is we have to have something that is continuous. And when we're dealing with continuous functions, if you recall, there are no interruptions. And no interruptions means there's no holes, jumps, gaps, anything along those lines. So it's our graph or function is not quote-unquote broken anywhere. And if you look at, these are just some examples of when a function has a discontinuity or is not continuous. If you notice, there's a discontinuity right here because of the open circle. If I come in and I'm graphing this function, I'm going to go up here and then I have to pick my pencil up to come down to this point and graph this piece. So I have another discontinuity. And here it tells me my function is continuous here. And then I have to pick up my pencil, drop down here to get a solution point, then pick it back up and follow my graph. So I have another discontinuity. So to sum up those three graphs, continuity fails when a function is not defined at a specific point, in this case at x equals c, if a limit does not exist at a specific point, or if the limit exists but it is not equal to the function evaluated at point C, and that would have been the third graph that we looked at on the previous slide. And if none of these conditions are true, then we say that our function is continuous. So the definition of continuity, and these are very, very important on your AP test. Sometimes you have to define continuity or prove that something is continuous based upon these principles right here. So a function is continuous at a point C if all three things are true. 1, the function has to be defined. 2, the limit as x approaches c of f of x does exist. And third, the limit as x approaches c of f of x must equal f of c. In other words, direct substitution. Okay, so continuity on an open interval. Okay, notice that this was at a certain point. Now we're looking at an open interval. Says a function is continuous on an open interval, defined with the parentheses, and then we have AB, if it is continuous at each point on the interval. Okay, and if it is, then we can represent it like this, and we say that it is continuous everywhere. If we have a discontinuity, we have two different types of discontinuities. One is a removable discontinuity. Now, a removable discontinuity is a function that can be made continuous by appropriately defining, or in some cases redefining, the function itself. And if you think, when we rationalized our numerators or when we factored, we were able to make a function that may have had one discontinuity continuous just by finding common factors and factoring that way and canceling things out so that we could then go back and recalculate. And then a non-removable discontinuity would be where your function is just flat up undefined. Okay, and an example of that would be like something like 1 over x, where you have either an asymptote at like x equals 0 or something like that. To go back to the graphs that we looked at earlier, this function right here, I could probably redefine this function so that I could quote unquote fill that in. So that would make this a removable discontinuity. The graph in part B has what we call a non-removable discontinuity. There's really nothing I can do to this function that would make these 2 points here join. I won't be able to factor out, I can't rationalize a numerator, there's nothing like that that I can do. And technically, if you look, your limit as you're coming in from the left, as x approaches c and you're coming in from the right, they're approaching two different things. So that's telling me right then and there that it's just flat out discontinuous. And then if we look at graph C, we see that we have a removable discontinuity because I could maybe replace this value right here up here, and then I can make one continuous line. So that would be another example of a removable discontinuity. So let's go ahead and look at example 1. Example 1 says that we want to discuss the continuity of each function. Well, if you look at f of x equals 1 over x, I know mathematically that x cannot equal 0, or I will have a discontinuous or a non-defined function. And again, because my function is approaching a different value as I'm coming in from the left as it is from the right, I would say that this has a non-removable discontinuity at x equals 0. If I look at part B, I have g of x equals x squared minus 1 divided by x minus 1. When we graph this, or even before we graph it, we just based on our denominator here, I know that I'm going to have a function that will be discontinuous when x is equal to 1, because that's going to make this whole function here undefined. But what I can do is I can rewrite that and make that x plus 1 times x minus 1 divided by x minus 1. These here are going to cancel, and now I can take the limit as x approaches my c value, or in this case 1 of x plus 1, and still get something that looks like this, but this point will now be filled in. Okay, now part C has a piecewise function, and if you look at this, because my piecewise gives me something that has a defined, or it has a defined domain, I have x plus 1 when x values are less than 0, which is this part of your function, less than or equal to 0. And then I have x squared plus 1 when x is greater than 0, which is right here. But because this right here overlaps, and I can include the point 0, my function is actually continuous all the way through. So there is no discontinuity here. This is a completely continuous function. Likewise, when I look at my trig function, y equals sine x, I can sit here and trace this function all day long and never have to pick up my pencil. So this would be another example of a continuous function. And now we're going to look at one-sided limits. If you recall from pre-calc, one-sided limits is just what it specifies. We're looking at one side of a limit, specifically the right or the left. So in this case here, I'm going to take the limit as x approaches c, and then I have this little plus sign. That plus sign means that I'm going to look at the right-sided limit. So the limit as x approaches c from the right of f of x is equal to L. In other words, what are my y values doing as x is approaching that c value? Likewise, over here, I have the limit as x approaches, and it looks like c negative or c minus f of x. Well, what that little negative sign really means is that we are looking at our left-sided limit. So I'm looking to see what my y values are doing as x is approaching that c value from the left. And sometimes one-sided limits are useful for taking limits of functions that involve radicals, as in this case right here. Now in example 2, it says to find the limit of f of x. So we're going to find the limit of f of x as x approaches a negative 2. So the square root of 4 minus x squared. As x approaches a negative 2 from the right, so I'm going to put this little plus sign behind that negative 2. And then equals, so as x is approaching negative 2, here's negative 2. And as I'm coming in from the right side of my function, going all the way over here, I notice that my y values are getting closer and closer to 0. So I'm going to say that my function then is equal to 0. Now, one-side limits are a lot of time useful when you're looking at the behavior of step functions. And I don't know if you've had this before, But one of the common types of step function is what we call the greatest integer function, and it's actually represented by like this little x that's in kind of a double bracket. This is known as our greatest integer function, and what that means is if I put a number something like 2.5 in, I'm going to round that to the next greatest integer, which in this case is 2. If I'm at a negative 2.5, then I'm going to round that to the next greatest integer, which would be a negative 3. So that's all this function is. And if you have seen these before, they kind of look like little stair steps as you go up. Now here is the definition for how we tell or prove that a limit actually exists. It says let the function f be a function and let c and l be real numbers. The limit of f of x as x approaches c is L if and only if both the left and the right limits are equal. If the left and the right limits are not the same, then the limit of the function as a whole will not exist. Okay, and it's very similar for the definition of continuity on a closed interval. Okay, except now we're looking as x approaches a from the right and b from the left, and it should equal our functions that are evaluated either at a or b. So if we look at example 4, we're looking at continuity on a closed interval, which closed just means that we're defined, and in this case we're going from -1 to 1. We are going to discuss the continuity of the function f of x equals 1 minus the square root of x squared. So in order to prove that this function is continuous, we have to 1, prove that the function exists as we're coming in from the left, as we're coming in from the right, and that if we evaluate the function at the actual endpoints, that those are also equal. So to do that, or to start out, let's look at the limit as x approaches, and we'll go -1 of f of x, and we want to look at, as we're approaching -1, we're coming in this direction, or in from the right, and our y values then are getting closer and closer to 0. Okay, so now I also have to evaluate my function at a -1. And if I plug a -1 in, I get 1 minus a -1 squared, which gives me 1 minus 1, which is 0. The square root of 0 is also 0. So because these two are the same, step 1 is complete. Now I'm going to go and look at this other point right here and say the limit as x approaches a +1 from the left, because now I'm going in this direction, of f of x is equal to, and I see that as my x values are getting closer and closer to 1, my y values here are also approaching 0. And if I do direct substitution, I have f of 1, and I plug a 1 in here. 1 minus 1 squared will give me 0. Square root of 0 is still 0. So my second part now says that because both of these are equal, I now have a continuous function on the interval from -1 to 1. And remember from pre-calc that these bracket looking things mean that my interval is closed. There are also a few properties of continuity. And the properties are very similar to the properties that we've seen in the past. It says if b is a real number and both f and g are continuous functions at x equals c, then we also know that we can have scalar multiples. So scalar would mean we're going to take that scalar and just multiply it by the function. I can add or subtract these functions. I can multiply them, and as long as the g of c function isn't equal to 0, I can also divide them. We also have a few functions that are always continuous on their given domains. So polynomials, okay, something like x squared plus, or ax squared plus bx plus c, something to the third power, the fifth power, doesn't matter. Any type of polynomial will be continuous. A rational function, which if you recall is just a polynomial divided by another polynomial. So as long as the denominator is not equal to 0, that will be continuous. Square root or radical functions are continuous. And then your 6 basic trig functions are also continuous within their given domains. Continuity of a composite function says if g is continuous at some point c, then the function f is also continuous, and the function f is continuous at g of c, then the composite function f composite g of x is equal to f of g of x. So these are also both continuous. So the last example that we're going to look at today, and this is really example 5, I apologize, says to describe the interval or intervals on which each function is continuous. Now, part A, we have f of x equals the tangent of x. B, we have a piecewise function. So let's go ahead and look at A. Now, when you graph the tangent, if you don't remember it, you can graph it on your calculator. Please be sure you are in radian mode. The one thing you know about the tangent is undefined in increments of pi over 2. So if I'm looking at something in between increments of pi over 2, I should have a continuous function. But at every increment of pi over 2, my function will be discontinuous. So if I get something that looks like this when I graph it, notice all these blue lines are our asymptotes. But if I'm going from like a negative pi over 2 to a positive pi over 2, or pi over 2 to 2 pi over 3, okay, we have continuous functions. So one way we could show this is by using this notation. I could go from a negative 3 pi over 2 to a negative pi over 2, negative pi over 2 to a positive pi over 2. These parentheses, recall, means that we do not include that point. If they were brackets, we do, but because we do not include our vertical asymptotes, we do need to use the parenthesis. And if we graph our piecewise function, we get something that looks like this right here. Okay? And the one thing I know is that at x equals 0, I do have a discontinuous function, but I do have a jump discontinuity, so I do have an alternative point that I can fill in. And how we would handle something like this is because I have that one discontinuity, everything out in this direction here is going to give us a continuous function, and everything out here will give us a continuous function. It's just that when x equals 0, we're going to end up with a discontinuous function. So our function then is going to be shown as being continuous on the intervals from negative infinity to 0 and from 0 to a positive infinity. And again, we include the parentheses and not brackets because parentheses means we do not include the point 0. And this is going to conclude part 1 for section 1.4 today. We'll continue on with the rest tomorrow. Have a great night.